Kohlrausch law of independent migration of ions. Limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. So first understand what is Kohlrausch law. Then we will talk about how we use it and why we use it. Limiting molar conductivity of an electrolyte means say NaCl can be obtained by individual contribution, means individual contribution of sodium ion and chloride ion. I said you need to send the assignment number, question number on WhatsApp. Okay. So which assignment question number you need to send on WhatsApp? So simply this equation tells you what is Kohlrausch law. The limiting molar conductivity of an electrolyte can be obtained by sum of their individual contributions, means individual limiting molar conductivities of sodium ion and chloride ion. Why it is required? It is required because in reality we don't use this equation as it is. Suppose we want to calculate the limiting molar conductivity of an electrolyte whose individual molar conductivities are not known, then we can use this. Okay. I will explain with examples. So in general, if an electrolyte on dissociation gives nu plus cations and nu minus anions, then its limiting molar conductivity is given by, means suppose CaCl2 is ionized in Ca2 plus and 2Cl minus. So in this case, mu plus is 1 and mu plus minus is 2. So that is what you have to understand. These are multiplied by their number of ions simply. Then you will get the limiting molar conductivity of the electrolyte, whole electrolyte. In previous case, we did not require this one because the ratio was 1:1. Now, weak electrolytes like acetic acid have lower degree of dissociation at higher concentrations, and hence for such electrolytes, the change in molar conductivity with dilution is due to increase in degree of dissociation and consequently the number of ions in total volume of solution that contains 1 mole of electrolyte. This is something you know. 1 mole of electrolyte has to be there. That's why we call it molar conductivity. What is important to know is that for weak electrolytes, there is low degree of dissociation at higher concentration, and hence for such electrolytes, change in molar conductivity with dilution is due to increase in degree of dissociation. Initially, it is very low at higher concentration. So if concentration is higher, here. Dissociation is low. If you decrease the concentration, the dissociation will increase and hence the number of ions will also increase here. So the increase in conductivity is due to increase in degree of dissociation and consequently the number of ions. If degree of dissociation increases means alpha increases, there will be more number of ions. More number of ions means the conductivity will increase. So at higher concentration, very low dissociation, degree of dissociation. Okay. So in such cases, lambda m increases steeply on dilution, especially near lower concentration. So once it is like this, but at lower concentration, it increases steeply. Because here in this region, the degree of dissociation increases very rapidly for weak electrons. So this is the graph for CH3COOH, blue color. Therefore, lambda m naught cannot be determined by extrapolation of lambda m to zero concentration. It will not give the lambda m naught. The zero concentration cannot give you lambda m naught because lambda m naught, according to this graph, will give us infinity value. However, for a strong electrolyte, if you see the graph for a strong electrolyte, you can get the lambda m naught very easy. For weak electrolyte at zero, you don't know what lambda m naught will be. Because these graphs may intersect, but even if these intersect, the point of intersection will not be very clear. So at infinity dilution, that is concentration zero, electrolyte dissociates completely, okay, alpha equals to 1. But at such low concentration, the conductivity of the solution is so low that it cannot be measured accurately. We cannot measure the conductivity accurately because we have diluted the solution at a very high degree, okay, too high dilution. We have added a lot of solvent into it, a lot of water into it. And when we have added a lot of water, still it is 1 mole of the electrolyte into it. But the number of ions in one region will be so low that measurement of conductivity will be not accurate. Therefore, lambda m naught for weak electrolytes is obtained by using Kohlrausch law of independent migration of ions. And what we do, we use the concentrations of strong electrolytes. How? I'll tell you. At any concentration C, if alpha is, this is actually alpha is the degree of dissociation, then it can be approximated to the ratio of molar conductivity at the concentration C to the limiting molar conductivity. Alpha is given by this formula. Degree of dissociation is molar conductivity divided by limiting molar conductivity. This formula you will be using. So note down and memorize. Degree of dissociation. But we know that for a weak electrolyte like acetic acid, Ka is given by C alpha square divided by 1 minus alpha. Substitute the value of alpha and you get another formula which you can use directly to get Ka in terms of lambda m and lambda m naught. Now there are two ways. Few students find it useful to first get the value of alpha. If lambda m and lambda m naught are given, then students find it useful that find the value of alpha from here and substitute that value of alpha here instead of using this formula. So it's up to you. And most of the teachers follow this approach. They first find the value of alpha and substitute the value of alpha here instead of using the formula directly. But this is important to know because questions will appear that if molar conductivity is increases, if it is this one, it increases, what will be the impact on Ka? So you can get the value directly from here in such cases if you know this formula. Okay, so four options will be given, which the answer you can find from this formula. Otherwise, you can first find alpha and substitute it. Using Kohlrausch law of independent migration of ions, it is possible to calculate lambda m naught for any electrolyte from lambda naught of individual ions. Now remember, capital lambda naught is for electrolyte. Lowercase Greek lambda is for ions, individual ions. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know the lambda m naught and lambda m at the given concentration C. We will be doing few numericals, then it will be clear. The question is calculate limiting molar conductivity of calcium chloride and magnesium sulfate from the data given in the table. In the table, H ion concentration, sodium ion concentration, potassium, calcium, magnesium, all concentrations are given and anion concentrations are given. Okay. So for calcium chloride, you need to apply the formula which we have seen here. Individual limiting molar conductivities will give you the molar conductivity of the electrolyte. So for calcium chloride, you need to use calcium limiting molar conductivity. So it will be CaCl2 will give you Ca2 plus 2Cl minus. So limiting molar conductivity will be 1 mu plus lambda naught of Ca plus mu minus lambda naught of Cl minus. It will be 1. There is only one Ca2 plus, so V plus will be 1. And lambda naught Ca2 plus is given here. Substitute it 119.0 plus. You have 2 Cl, so you will write twice of Cl minus 76.3. Solve it. You will get the answer as 271.6. Okay. Similarly for MgSO4. Just confirm whether you are able to listen to me or not. If anyone can confirm. Okay, what I was talking about, that similarly you can get the limiting molar conductivity of MgSO4 also. For MgSO4, again the reaction will be similar. MgSO4 will give you Mg2 plus SO4 2 minus. So one cation, one anion. So again lambda m naught will be 1 multiplied by magnesium 106.0 plus number of cations 1 SO4 SO4 2 minus 160. So you will get 266, 106 plus 160 will be 266. That will be the answer. Simple questions. These are simple questions, but slightly typical questions will be there. We will be talking about. Okay. Yes, Shashwat, correct. Rashi, yes, that's what it means. Correct. Next question, and this is a typical question which will appear in your examination. Lambda m naught for NaCl, HCl, sodium acetate. This is sodium acetate. Are given. Calculate lambda m naught for acetic acid. HAC is acetate, this part, and H, acetic acid. So first write what is given, and then we will see how we can calculate the answer. So lambda m naught NaCl. Lambda m naught NaCl is given, or it is written like this also, NaCl in bracket, 126.4. I'm not writing the units, Siemens centimeter square per mole. Then it is given lambda m naught HCl, 425.9, lambda m naught CH3COONA, 91.0. I am not writing the units, you need to write. Okay. So 126.4, 425.9, 91.6. And what you need lambda m naught of HCl. And lambda m naught of HCl will be H plus Cl minus, means lambda naught of H plus lambda naught of Cl minus. So this is what you need to find out with the help of these things. And these things you can write like this will be lambda Na, lambda Na plus naught plus lambda Cl minus naught equals to 126.4. Say this is 1. Say this is 1 what we need to find out. Say this is second. Now find from here, sorry, it was not, we need to calculate this, not HCl, rather we need to calculate for HAC, sodium acetate, acetic acid. So we need to calculate lambda m naught for acetic acid, CH3COOH. Means we need lambda m naught of CH3COOH as lambda CH3COO minus naught plus lambda H plus naught. This is what we need. And what is given? Lambda NaCl is given. Then lambda HCl is given, means lambda H plus naught plus lambda Cl minus naught. It is given as 425.9. Say this is third. Then this is given. This is actually lambda CH3COO minus naught plus lambda Na plus naught. This is given as 91.0. Say this is 4. Now your job is to find the required one. The required one is this. We need this one. From these three. And this is something as per the Hess law, similar to Hess law, which you have used in thermodynamics 11th grade. So you need to rearrange, multiply like that, subtract, add, and get the final equation. Now, how do you get it? You actually need this one. It means this has to be positive. Wherever you have CH3CO minus, that will be positive. It means this reaction will be positive. So write it as it is, 4. Then you need H plus also, that will be positive. So H plus you have here in third, right third plus. Now when you add these two when you add, apart from what you need these two, you will have these extra, Na plus and Cl minus extra. It means you need to subtract this equation, second one, because second one has Na plus and Cl minus. So subtract this one, second one. You will get first one. If it is not clear, let me know, because these type of questions normally appear in your examination. Okay. I have already got few answers. Shashwat, Shivangi, Ashi, Preeta, Ahan. Yes, good. Yes, I will explain again. Okay. I'm explaining it with just, so this answer I have got from 5, 6 students. Okay, same answer. Understand what this question says. This question says that limiting molar conductivities for NaCl, HCl, and sodium acetates are given. We have to find limiting molar conductivity of acetic acid. And acetic acid is weak acid. Normally, for weak acids, as we have talked about, it is not possible to calculate limiting molar conductivity. For that, we use limiting molar conductivity of other acids and salts and try to form the Kohlrausch law equation. For this one, Kohlrausch law equation, we need. So I am writing first Kohlrausch law equation for this one, NaCl. It is given. Okay. So we will say for NaCl, lambda m naught NaCl will be lambda Na plus naught plus lambda Cl minus naught, and it is given as 126.4. Say this is first equation. Similarly, now for HCl, lambda m naught HCl will be lambda H plus naught, means individual ions limiting molar conductivity, plus lambda Cl minus naught. It is given as 425.9. Say this one is second. Now for sodium acetate, this is lambda m naught of CH3COO sodium acetate. This will be lambda CH3COO minus naught plus lambda Na plus naught, and it is given as 91.0. These three are given. So we formed these three equations. Now talk about the required one. Required one is for acetic acid. HAC is acetic acid. So for acetic acid, it will be lambda CH3COO minus naught plus lambda H plus. And this is something you have to find the value. How from these three you can get the required one? You need lambda CH3COO minus. It means this equation you need to use as it is. You need CH3CO minus. So this will be equal to lambda m CH3COO Na, this one, okay, means third equation you need. You also need lambda H plus, and lambda H plus is here. It means you need to add this one into third one. So you add second one. But when you added these two, what you got? You got, when you added third, you got this one, means lambda CH3COO minus plus lambda Na plus naught. And then you added this one, lambda H plus naught plus lambda Cl minus naught. It means what you required these two are there, but you have Na plus and Cl minus extra. These two in squares are extra. It means you have to deduct this. You have to subtract lambda naught Na plus and lambda naught Cl minus, which is actually this one, the first one. So if you subtract the first one, you will get just lambda naught CH3CO minus plus lambda naught Cl minus, lambda naught H plus. Okay. These two you will get, and these two are required. Is this clear now, Yastika? Okay, so this is application similar to Hess law. How to get the required equation. It means it will be third. Third is 91 plus second. Second is 425.9 minus first. First is 126.4. When you solve this, you will get 390.5 as the answer. Next question. The conductivity of 0.001028 mole per liter acetic acid is given. Calculate the dissociation constant and conductivity if lambda m naught for acetic acid is this. Answer is very easy. First, I am looking for who can give me the answer. Dissociation constant is asked. Okay. Yes, Ashti, that is the formula we will be using there. Conductivity is given. Okay. Conductivity. What is conductivity? What is the sign of conductivity? Do you remember resistivity, conductivity? Fine. Concentration is given C. C is given. Conductivity is given. Limiting molar conductivity is given. Dissociation constant you need to find. Okay, they were, I think you are in the right direction. Tell me the answer. One, yes, good. Okay, molar conductivity is kappa by C. Okay, the point here you need to remember that C you can use in moles per cubic meter, but lambda m naught is given in centimeter square. So don't forget to convert that into per centimeter cube instead of meter cube. And then calculate the answer and let me know. After that, I'll solve it. Answer is something different, I think. Okay. And unit will be, okay, I think probably by, that is typo. That should be centimeter square. Anyway, just I'm giving you hints. Kappa by C. Okay. Yes, value of alpha is correct. Yes. Then alpha you can calculate lambda m by lambda m naught. After that, K is equal to C alpha square divided by 1 minus alpha. And because it is acetic acid, you can write just C alpha square also. That will also give you approximately correct answer. For very weak electrolytes, K is equal to C alpha square. Alpha in the denominator can be neglected. If it is too low, okay, only then, otherwise not. Okay, let me check whether your answers are correct or not. Let me see the answers. Alpha value correct and 1.78 into 10 power minus 5. Yes, Ahan, Ashi, correct. Theta seems you have not converted the meter cube to centimeter. The mixed units probably. Expecting a few more answers. Solve it quickly and tell me the answer. Giving you 30 more seconds quickly. Tell me the answer. Okay, Shivangi, I'll explain. Vanna, yes, good. Okay, first understand. There are a few formulas you need to remember. If you want to solve such questions, basically it is application of some formulas we have used earlier. Okay. So for that, we know that for dissociation constant, that is K, C alpha square upon 1 minus alpha, we need alpha. This is something is asked. For that, we need alpha. And alpha is molar conductivity divided by limiting molar conductivity, means we need lambda m. And lambda m we get from kappa by C. Kappa by C. Now remember here it is mole per liter. Answer is in mole per liter. Here it is centimeter square. So you need to be cautious here. So suppose if I write kappa here, which is given as conductivity, is given in centimeter. 4.95 into 10 to the power minus 5 divided by 0.001028. What will be its unit? Its unit will be Siemens per centimeter per mole liter, because this is in denominator. It will be per mole liter. Okay. Now, if you calculate alpha, and alpha will be lambda m by lambda m naught, this is given in Siemens centimeter square mole inverse. So by what factor you need to multiply? Which factor you need to consider here? And why also? Why also? No answer received till now. My question is, do you need to repeat it by a factor? This value of lambda m, do you need to multiply by it some factor or not? Yes, by what factor? This is something I had shown you in previous class. I had shown you the formula also, that if you are using mole per liter, okay, it is not cubic meter. If you are using mole per liter, you need to multiply it by 1000. Okay, so that formula, I will have to go back a lot, but I want to still show you that in that case, you will use this formula. You need to multiply it by 1000 if you are using liters, and that is the common mistake. Okay, so here also see we are using liters. So because we are using liters, it will not be just kappa by C, which you need to pay attention. It will be 1000 into kappa by C. That will be the correct lambda m. Okay. So when you multiply, you will get 48.15. 48.15. Same units, Siemens centimeter square mole inverse. Now you can get alpha as lambda m by lambda m naught. That is 48.15 divided by lambda m naught is given 390.5. When you divide, you will get 0.123, this value. From here, you got alpha. The moment you got alpha, substitute it. You got alpha from this formula. Now substitute alpha here. You will get the answer. Okay. Concentration C is anyway given in mole per liter. So this is the same thing you will substitute here because here concentration is used in mole per liter. So that's something you can do. Now the question, why does the conductivity of a solution decrease with the dilution? This is something we talked about in previous class. So you can quickly answer this question. Conductivity, not molar conductivity. Why does the conductivity of a solution decrease with the dilution? Yes, Archie, correct. Ashwat, correct. Okay, so conductivity is always per unit volume. So whenever we talk about conductivity, it is conductivity per unit volume. If we increase the dilution, okay, with dilution means dilution is increased. So if we increase the dilution, the number of ions present in the same volume as compared to earlier unit volume decreases, although total number of ions will increase on dilution, but per unit volume it will decrease within the same volume. So if initially the volume is this much and now the volume is this much, initially say this one was the unit volume. So here total number of ions were 1/4 of total, say, right? Now in the same volume, although number of ions, total number of ions will increase, but in this region only, it will decrease as compared to earlier. So because number of ions per unit volume decreases, that's why the conductivity decreases. Unit volume is the key word you need to include here. So go through the answer, then I'll move to next part. Next question, suggest a way to determine the limiting molar conductivity value of water. Think about it, write the answer in chat box. For water, Ashi, it will be lambda H plus naught plus lambda OH minus naught. Okay, now my question is, before that, I should see what Shivangi has written. Mm, yes, Shivangi, you are in the right direction. Now, water is very weak electrolyte, and we talked about that for very weak electrolytes, it is not possible to calculate lambda m not directly because it will be just approximate. We can't calculate exact value because on dilution, the conductivity increases very rapidly. towards high dilution, conductivity increases very rapidly. So exact calculation of lambda m naught is not possible. So now tell me, Divya, that is the, yes, that is the equation you will be using, but you can't use lambda h plus naught plus lambda h minus naught directly. Yes, Ashi, now you are in right direction. It's still a little bit you need to change, but you are in right direction now. Shivangi in right direction, Ashi in right direction. One, yes, you got it right. Yes, you need H plus and OH minus. You need, but you can't use these directly. You need this, okay? Because lambda m naught for water, it will be this. So for that, you need one strong electrolyte which has H plus, another strong electrolyte which has OH minus, and then the third one which can be subtracted to get rid of the other ones. So one electrolyte which has a strong, but a strong electrolyte which has H plus is HCl. One strong electrolyte which has an OH minus is NaOH. So we have H, we have OH, but now to remove this, we need NaCl also. So HCl plus NaOH minus NaCl. Did you get it or not? What I am saying? You need H plus and OH minus. For that, you identified a strong electrolyte. For a strong electrolyte, it is possible to calculate limiting molar conductivity, right? Is that clear or not? Good. So HCl is strong electrolyte with OH minus NaOH. But when we add these two, we get H plus and OH minus, but we get this extra. For this one, we will subtract NaCl. It means lambda m naught of H2O will be lambda m naught of HCl plus lambda m naught of NaOH minus lambda m naught of NaCl. This is the way we will calculate, we will determine lambda m naught of water. Okay. If still there is any confusion, you can let me know. Next question. The molar conductivity of 0.025 mole per liter methanoic acid is given. Calculate the degree of dissociation and dissociation constant. Given individual limiting molar conductivity of H plus and individual limiting molar conductivity of oic acid, HCO minus 54.6. Question is easy. We have done these type of questions. Tell me the answer. Solve it. And everyone has to send this question because we have done these type of questions. You should be able to solve. Everyone should be able to solve these type of questions. You have to send the solution to me after the class. Right now, you have to tell me the answer. After the class, you need to send the solution to me. Approach is similar. Calculate lambda m naught from the given values. Molar conductivity is given. In this case, lambda m is given. So C is given 0.025 mole per liter. And remember, if you use mole per liter, the formula will be kappa 1000 by C. Okay? Although here it might not be required. Lambda M is given 46.1 Siemens centimeter square per mole. Lambda M naught will be lambda H plus naught plus lambda HCOO minus naught. These values are given. So you got lambda M, you got lambda M naught, you got the value of alpha. Once you got the value of alpha, you got the value of K. C is given. Preeta Ahan, value of alpha is correct. Good. Shivangi Ashi, yes, correct. Answers. Yes, Shivangi. So from here, you will calculate the value of alpha, lambda m divided by lambda m naught, and after that, k equals to c alpha square divided by 1 minus alpha. You will get the answers. Yes, correct answer. Now, electrolytic cell and electrolysis. A few more concepts about these. Now, in an electrolytic cell, external source of voltage is used to bring about a chemical reaction. Now, it is opposite of galvanic cell. From galvanic cell, you get the electricity. In electrolytic cell, what you do, you have the external potential in reverse direction and greater than the standard electrode potential of the cell. So a galvanic cell can be converted to electrolytic cell. So suppose you have a cell and this is anode, this is cathode. Remember always the convention, right side will always be cathode, left side will be anode. And there is some electricity flowing from cathode to anode, and there is a salt edge. So this is galvanic cell. This is galvanic cell. But suppose you have a battery here, and in opposite direction you apply the voltage and greater than its EMF. Then direction of current will change and the reaction will also change. Reaction will be reversed. Okay? Reaction will be reversed. So one of the simplest electrolytic cell consisting of two copper strips dipping in an aqueous solution of copper sulfate. Just a second. If a DC voltage is applied to the two electrodes, then Cu2 plus ions discharge at the cathode negatively charged and the following reaction takes place. Remember, we are talking about cathode. Okay? Cathode reduction will take place. Copper metal is deposited on the cathode. As the at the anode, copper is converted into Cu2 plus ions by the reaction, oxidation reaction. From 0 oxidation state to +2 oxidation state, it is oxidation. So at anode, there will always be oxidation. At cathode, there will always be reduction. So two compartments will change, right? Their nature. So in galvanic cell, where reduction was taking place, their oxidation will take place. So cathode will become anode, anode will become cathode, but conventions will not change. At cathode, reduction will take place. At anode, oxidation will take place. So the copper is dissolved or oxidized at anode and deposited at cathode. This was the case in case of galvanic cell also. At anode, copper was getting dissolved or zinc was getting dissolved in that case. If you remember the Daniel cell specifically. So at anode, metal is dissolved. At cathode, metal is deposited always, whether it is galvanic cell or whether it is electrolytic cell. Quantitative aspects of electrolysis, and here numerical appears from here. Okay. So first law of electrolysis, which is known as Faraday's first law, the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of the electricity passed through the electrolyte. You can memorize this. The amount of chemical reaction which occurs means how much chemical reaction occurs. Amount of chemical reaction means how much chemical reaction will occur at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte. How much electricity is passed, that much chemical reaction will take place. Less electricity passed, less chemical reaction, more chemical electricity, more electricity, more chemical reaction. So it is straightforward. Second law, the amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. Atomic mass of metal divided by number of electrons required to reduce the cation. You need to remember equivalent weight normally in CBSC is not used. CBSC normally equivalent weight normality questions you will not get. Okay, you will get only in JEE mains and NEET, not in JEE advanced. For equivalent weight you need to remember at least this much formula, that atomic weight of the metal divided by number of electrons required to reduce the cation in balanced direction. So it is the same thing where we talked about n, value of n in Nernst equation. Yeah. So for example, in Daniel cell, this value will be 2. 2 electrons are required to reduce the cation. Because in Daniel cell it was Zn2 plus 2 electrons will give you Zn metal. So equivalent weight will be half the atomic mass in that case. So again, second law, the amounts of different substances liberated means how much substances are liberated by the same quantity of electricity passing through the electrolytic solution. These are actually proportional to their equivalent weights. If equivalent weight is more amount will be liberated. If equivalent weight is less amount will be liberated. Atomic mass is not considered here. Atomic mass might be higher, but atomic weight can be lower. Atomic mass equivalent weight can be lower. The reason is atomic mass divided by the electrons transferred gives you the equivalent weight. What I am saying, try to understand. Suppose I am talking about two cases. In first case, the atomic mass is say 90 or say 40, and in second case, atomic mass is 60, say. Okay? So it is not proportional to atomic mass. We won't say that the amounts of substances liberated will be proportional to atomic mass. So in this case, it will be here amount will be less, here amount will be more if it is based on atomic mass. But suppose here electron transferred is just one and here electron transferred two. Then here equivalent weight will be 40 divided by 1, that is 40. However, here equivalent weight will become 60 divided by 2, that is 30 only. Now, in this case, equivalent weight is higher here, which actually decides the amount liberated. So it is equivalent weight for less atomic mass can be higher. Okay. So an element can have less atomic mass, but higher equivalent weight than the other one, which has actually higher atomic mass. These two laws sometimes are asked in assignments also. These are asked as questions, so you need to memorize, write and memorize. Yes, Yastika, that depends on the number of electrons, so that's why number of electrons in the picture. Yes, Divya, it is reverse of galvanic cell. Write down and memorize the definitions of first law and second law. Okay. A quantity of electricity is given by Q. Q equals to IT, which I hope by now you have studied in physics. Q equals to IT. The charge is equal to current multiplied by the time the current flows. Q is in coulombs, current in amperes, and T in seconds, SI units. The amount of electricity or charge required for oxidation or reduction depends on the stoichiometry of the electrode reaction. For example, stoichiometry of the electrode reaction means how many electrons are required in balanced, how many moles of electrons are required in balanced equation. Okay? So for example, in this case, Ag plus E minus gives you Ag, it is just 1:1 ratio. 1 mole of electrons is required for the reduction of 1 mole of silver ions. 1 mole of electrons required for 1 mole. Charge on 1 mole of electrons will be equal to 1 Faraday. You remember 96487 we talked about, which is actually charge on 1 mole of the electrons. So when you multiply charge of 1 electron by 6.022 into 10 power 23, that gives you charge on 1 mole of the electron, 1 Faraday. This quantity is called Faraday and is represented by symbol F also. So that's why in that equation, last equation, it was RT by N F. This F was 96487. For approximation, you can use this one. And to make the calculations simple, you are advised to use this unless it is some objective type question and their values are too close. If values are too close to each other, then use exact value. Otherwise, 99% cases you can use different approximate. Now the question based on it. A solution of copper sulfate is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited at the cathode? First, think about it. Previous slide, Shivangi, this one. This is the same thing I talked about during Nernst equation. Solve this question, or at least try to solve, try to understand before I explain. You can calculate the amount of charge, you can write the balanced equation, and pay focus to the number of electrons and relate it to Faraday, 1 mole of electrons. I'm giving you a hint. Okay, just hint. What is the mass of copper deposited at cathode? So it will be Cu2 plus 2 electrons will give you copper solid. It means 1 mole of copper is deposited by 2 into 96487 coulombs. Okay. Yes, Vanna, correct. Charge is correct. So for that, you need to calculate this much charge will deposit how much. So from here, you got the charge Q equals to IT. I is 1.5 ampere and T is 10 into 60 seconds. Remember, time is in seconds, I is in amperes. So 600 into 1.5, 900 coulombs. So if these many coulombs deposit this much, then 900 coulombs will deposit how much? That will be the answer. First, try it. It is simple. Okay. You know that the amount of second law, I am talking about second law, amount of the products deposited will depend on the charge. Okay. Amount of electricity. The amount of electricity, you know, 900 coulombs you have. So you have to find this 900 coulomb will deposit how much copper. For that, you need to know the relationship. And relationship, you know that 2 into, that is 2 moles of electrons deposit 63.5 grams. So you will write as 2 into 96487 coulombs of charge deposit 63.5 grams of copper. 63.5, why? Because 63.5 is the atomic mass of copper. That's why 1 mole of copper is 63.5 grams. So 2 moles of electrons deposit 1 mole of copper. 2 moles of electron you will convert to charge. 2 into 96487. 1 mole of copper you will convert to mass because that is asked. Hence, 900 coulombs of copper will be deposited by 63.5 divided by 2 into 96487 into 900. That will be the answer when you solve. Okay, let me see who is giving me correct answer calculation wise.